Kia ora and welcome to video 6 in the series Delightful Differentiation. Shout out to any of my fans down in the Bay of Plenty. That's where I hail from. You might have noticed the shirt, the blue and yellow stripes. This week we're going to cover off 5 more questions. We've got a couple of guest presenters joining us. In this question we've got a function that involves the absolute value symbols. I'm absolutely pumped for this video. I had to do it, I'm sorry. So here we go. It's a pretty simple problem. We're finding the absolute maximum of it. Be careful of the wording there. It says absolute maximum, which is slightly different, as I'll explain later, to relative minima or maxima. The reason I've included this video in the series is because students are notoriously poor at working with the absolute value. If you have never seen those symbols before, you might be thinking they look kind of like modulus symbols in complex numbers, and they behave similar. The absolute value of x, what does that actually mean? These symbols down here, it just means that if x is negative, the absolute value turns the x into a positive number. For example, the absolute value of negative 3 is positive 3. The symbols do nothing if x is positive, like the absolute value of 7 is just 7. Anyways, give this a go before you watch the solution, and I hope you enjoy it. All the best. Okay, normally when we're finding the maximum of a function, we differentiate and set the gradient function equal to 0 because we're finding stationary points. I've cheated. I've had a look at the graph on Desmos. You could do the same on your graphics calculator if it's an exam. And we see that the graph has got 3 sections. The absolute maximum of the function's actually where the gradient is undefined. You can see it's pointy at the top. It's kind of like a tent, a circus tent. The minimum, however, would be a stationary point to the graph where the gradient equals 0. But if we weren't to know that, and we haven't looked at the graph, then we're going to set the derivative equal to 0 and have a look. So the 3 sections come about because the absolute value behaves differently if x is negative. So our first case could be if we consider x is greater than or equal to 2. And when x is greater than or equal to 2, the absolute value symbol does nothing in this function. Like the absolute value of a positive number is just that positive number. So we can just consider the function 1 over 1 plus x plus 1 over 1 plus x minus 2. We can get rid of the absolute value symbols. Now if I look at Desmos here and I graph this function, so we've got 1 over 1 plus x, and then we're adding 1 over 1 plus x minus 2. We can see here how it's a pretty strange function, but it corresponds to the original function for x is greater than or equal to 2. Okay, so differentiating this expression, we could put the fractions together and then use the quotient rule, or we could use the chain rule. How about I just use the chain rule because it's, I guess, already set up and easier to do that. 1 over 1 plus x is the same as 1 plus x to the minus 1. So differentiating that, we get negative 1 over 1 plus x all squared. Power comes down the front as a minus 1, the power drops to a minus 2, then we times by the inner function differentiated, but in this case x plus 1 differentiates to 1. The other one is 1 plus x minus 2, which simplifies to x minus 1, so it's x minus 1 to the negative 1, which will differentiate to minus 1 over x minus 1 all squared, and we want to make that equal to 0. We kind of know what I'm going to get here. I'm going to get no turning points because x is greater than or equal to 2. The function has no points where the gradient equals 0. We can kind of see that in the structure of this equation because it's negative a perfect square and then it's negative another perfect square. So this is never going to be equal to 0, but if we didn't spot that, we're going to be trying to solve this expression. Move one of the fractions to the other side, cross multiply, and then maybe expand out. Negative x squared plus 2x minus 1 equals 1 plus 2x plus x squared. 2x's cancel. We end up with minus 2x squared equals to 2. So negative a perfect square equals 2.
That's only true if x is imaginary, and of course x is real for this particular graph. So no real x. Okay, no stationary points. Now, to save us some time, I would do that for the case where x is less than or equal to 0. That maybe is my case 2. X is less than or equal to 0. I would get the same result. So really I'm just considering the values in between 0 and 2. So case 3, if x is in between 0 and 2, looking at the function, this part of it, the absolute value symbols will do nothing, but the other part, this dude here, well, if x is between 0 and 2, then x minus 2 is negative, and therefore the absolute value symbols turn that negative into a positive. So our function becomes 1 over 1 plus x like it was before, but the second part is 1 minus x minus 2. Okay, the absolute value symbol, to get rid of it, we need a minus in the front. And that's our function. So again, trying to find stationary points by differentiating. Same as before, minus 1 over 1 plus x squared for that first part. This next part is 1 over 3 minus x. Okay, 3 minus x to the negative 1. So using the chain rule, differentiate the outer function. Minus 1 comes down, power drops to a negative 2, so we're going to get 3 minus x all squared. Then we times by the inner derivative, which is negative 1. Be careful of that, otherwise you'll come to the conclusion there's no stationary points again. Equals 0. Do the same thing as we did before, leave 1 on one side, move the other to the other side, being careful with the double negative. So it's a positive, but then moving it to the right, it's a negative again. Divide both sides by negative 1, cross multiply. And all of this is just going to get us an answer that's the minimum, which is a bit of a pain. But then we need to reflect on the answer and go, well, does it even have a maximum? Cancel the x squareds. 8x equals 8, x equals 1. Right, so we could do a little bit of extra work using calculus to prove that's a minimum. We could do a second derivative test and substitute x equals 1 into it. We could look at the graph here and see it's a minimum, but I'd rather not use a second derivative test. Could just use the first derivative test. So choose a value of x, either side of 1 that's close enough. So I don't know, something like 1, negative, don't need a negative there, my goodness, 0.9 and 1.1. So at x equals 1, the gradient is 0, and then substitute 0.9 into the gradient function that we've got up here. Oh, actually no, is it? Yes, yeah, it's the same gradient function because in between 0 and 2, the function doesn't change. So yeah, it's that gradient function. Sub in 0.9 into it, and you'll find that it's a negative. Sub in 1.1 into it, you'll find it's a positive because the graph goes like that. So it's going down, then 0, then back up. That's our first derivative test, and that will tell us it's a minimum. Now, there's a key bit of wording in the question, and the question says, find the absolute maximum. So on a graph, when we find stationary points, we're finding a local minima, whether it be a minimum or a maximum, local stationary points. What we need to then consider is across the whole interval, whether that is actually the smallest value or the biggest value. Because we can get functions like, let's say a cubic that goes like that. Now that there's a local maximum, but it isn't the maximum. In fact, there is no absolute maximum if it goes on forever. If the cubic had a restricted interval, so something like that, where it ended at a certain point, that's the local maximum, but the global max is actually at the end point. So we need to consider endpoints or points where the gradient is undefined, as I was mentioning earlier. So let's look at this graph here. The function, we're given no restricted interval, so it goes off to infinity or to negative infinity. therefore no global maxima or minima at the end points, but looking at the change from one function to the other, that is where the function gets its highest. So checking x equals 0 and x equals 2 where the function changes its behavior, we get f of 0 equals to 4/3. That is the max. Again, you could kind of do like a first derivative test on this. You could say the gradient is increasing upwards to x is equal to 0. At x equals 0, the gradient is undefined because it can't have two different values. You know, like if you're on the left of x equals 0, the gradient's increasing. If you're on the right of gradient x equals 0, you're decreasing, at least up to the point x equals 1. So in between there, it goes from going up to going down. But at x equals 0, the gradient is undefined because it has two different values depending on what you do with the absolute value symbols. So the absolute value symbols do nothing for x slightly bigger than 0, but for something slightly less than 0, it would turn into 1 minus x in the denominator, so a different function. It's easy to see that on the graph, I guess. Okay, so we've got a gradient going up and a gradient going down afterwards. There the gradient is undefined. And we also need to consider those points when we're thinking about maxima or minima. Hopefully that made sense. It's kind of a sneaky question because normally with functions you just go about making the derivative equal to 0, and also hopefully that's helped you understand how the absolute value symbol works and how if we want to differentiate a function like this, we need to consider different cases depending on the value of x or the value of the thing that's inside the absolute value symbols.